to inject quantum mechanics into our understanding of things like black holes, and that's where Hawking proved that black holes are not completely black. Astrophysics, the branch of science that seeks to understand the universe and the way it works, has long been interested in the mysterious concept of black holes. Black holes are regions in space with such immense gravitational pull that nothing, not even light, can escape from them. Their existence was first theorized through Einstein's theory of general relativity in the early 20th century, and over the years, extensive research and observations have reinforced their significance in our understanding of the cosmos. One of the tools researchers used to figure out the realities of space is the James Webb Space Telescope. While it wasn't meant to study black holes, since the focus is on the entirety of observable space, it's bound to pick up information about black holes too. But the problem is that the information it's picked up is the exact opposite of what we were expecting. Brian Greene has just confirmed the recent finding, and it turns out, according to the James Webb Space Telescope, black holes aren't real. Join us as we bring you all the details. Telescopic imagery from the Event Horizon Telescope of the black hole in M87, which ripped on the fabric of space, was the most direct evidence about this shocking discovery and how it's turned the world of science upside down. Black holes are cosmic entities predicted by Albert Einstein's theory of general relativity. According to this theory, the massive objects form the entire fabric of spacetime, creating what we perceive as gravity. When a star runs out of its nuclear fuel and undergoes a supernova explosion, its core collapses under the sheer force of gravity. If the remaining mass exceeds a critical limit known as the Chandrasekhar limit, the gravitational collapse becomes irreversible, leading to the formation of a black hole. But even with that, black holes have always been theorized about since their initial discovery. While black holes themselves can't be directly observed because of the way they're created, scientists have identified several key characteristics and properties through indirect observations. As light from background stars or galaxies passes near a black hole, its path is bent by immeasurable gravity, creating a gravitational lensing effect. While it sounds absolutely trippy, it's the only thing that allows astronomers to detect and study black holes indirectly by actually studying their gravitational influence on surrounding objects. So what's around the black hole is very important here. When matter from nearby stars or gas clouds falls toward a black hole, it forms an accretion disk around the black hole. These vibrations created by the black hole ripple through the gas cloud. These vibrations are then picked up on planet Earth, massaged by a computer, and amplified by 57 octaves. The material in the disk becomes superheated and emits X-rays, providing another observable signature of black holes. The vision or interaction of black holes with other massive objects can produce gravitational waves, ripples in spacetime, which were directly detected for the first time in 2015. So, there are both very old and new observations that have been made over time. Over the decades, extensive astronomical observations and advances in technology have provided quite compelling evidence supporting the existence of black holes. Gravitational lensing has offered a look into the distorted light from background objects, indicating the presence of massive objects with intense gravitational fields. Plus, X-ray emissions from accretion disks around invisible objects have matched theoretical predictions for black holes. Not only that, but the detection of gravitational waves, specifically from the merger of black holes, has provided direct confirmation of these powerful entities. The James Webb Space Telescope is a technological marvel that was created to revolutionize astrophysics, and it has not disappointed in its mission to uncover the secrets of the cosmos. As researchers eagerly waited for its data, they were not prepared for the astounding revelations it would bring. Armed with this state-of-the-art observatory, scientists went on a journey that led them to make extraordinary claims that challenged the very existence of black holes. Yes, researchers utilizing just data have reported intriguing phenomena that appear inconsistent with our traditional understanding of black holes. Some of these findings have pointed to the possibility of alternative explanations for the things we always thought were proof of black holes. Well, let's just say that the world of space exploration has done a complete 180. One of the problems has to do with gravitational lensing. With the JWST's advanced observational capabilities, researchers were expected to witness familiar gravitational lensing patterns that align with our understanding of black holes. The light should bend, and there should be that big black hole of nothingness that's causing light to distort. However, some of the observed gravitational lensing events presented strange results. You know, when matter falls toward a black hole and forms an accretion disk around it, the superheated material emits X-rays, which are detectable by telescopes. These X-ray emissions are among the key observable signatures used to identify black holes and study their properties. If the black hole's mass goes up by the amount of mass that falls in, even that concept is being turned around on its head. With the JWST, scientists have scrutinized regions suspected to contain black holes, observing their X-ray emissions in greater detail. Unexpectedly, certain black hole candidates have shown peculiar patterns in their X-ray emissions that challenge the conventional understanding of these cosmic entities. The expected variations in X-ray brightness, spectral characteristics, or timing properties have left researchers wondering if traditional black hole models adequately account for these emissions. This uncertainty has given rise to alternative explanations that explore the possibility of other exotic compact objects or modified gravity theories. One of these has to do with gravitas, hypothetical objects that have captured the imagination of astrophysicists as they present a unique twist on the classic black hole theory. In the gravity model, the exterior still appears similar to a black hole, following the well-known metric that describes gravity's behavior around such massive objects. However, a fascinating twist lies within its core. Instead of a singularity like the one postulated in traditional black holes, gravitas has a more distinct metric inside. What takes things even further is its event horizon, which hosts a thin shell of matter. This peculiar configuration sets gravitas apart from conventional black holes and prompts scientists to consider intriguing possibilities. The Laser Interferometer Gravitational Wave Observatory, LIGO, has also played a pivotal role in our overall journey to explore the cosmos, detecting gravitational waves from distant cosmic collisions. LIGO has allowed valuable insights into the nature of compact objects. Plus, in some instances, the gravitational waves detected by LIGO have also exhibited characteristics that are completely indistinguishable from those of ordinary black holes. So, something is going on here in the realm of astrophysics and general relativity. The no-hair theorem has long stood as a prominent principle shaping our understanding of black holes. According to this theorem, all stationary black hole solutions to the Einstein-Maxwell equations, which describe the gravitational and electromagnetic forces, possess a unique set of characteristics. These specific attributes are the black hole's mass, angular momentum or spin, and electric charge, collectively referred to as the black hole's hair. The no-hair theorem suggests that any other distinguishing features of a black hole, beyond its mass, spin, and charge, are considered hair and are believed to be lost beyond the event horizon. This event horizon acts as an impenetrable boundary beyond which information is seemingly irretrievable from an external observer's perspective. To put it in one sentence, conventional black holes have been thought of as relatively simple and devoid of any further distinguishing properties. However, in a remarkable study, Sasha Hako, Stephen Hawking, Malcolm Perry, and Andrew Strominger challenged this traditional view of black holes. Their groundbreaking research presents the existence of what they call soft hair in black holes, suggesting a more complex structure than anyone previously thought. Soft hair refers to a collection of quantum properties that are thought to reside on the black hole's event horizon. Unlike conventional hair, soft hair is not associated with the black hole's mass, spin, or electric charge. Instead, it is believed to have subtle quantum properties that encode information about the black hole's interactions with its surrounding environment. The existence of soft hair would have profound implications for our understanding of black holes and the nature of information in the universe. It could potentially resolve long-standing questions related to the information paradox, concerning what happens to the information of matter that falls into a black hole. The idea of soft hair hints at the possibility that black holes may retain subtle quantum fingerprints of their past interactions, raising the exciting prospect of retrieving information that was once thought lost beyond the event horizon. And if that's true, then what the James Webb Space Telescope found would be true too. But if you reel things back in time a little bit, this concept has actually been around for a really long time. Back in 1974, Stephen Hawking proposed a groundbreaking idea called Hawking radiation. According to this, black holes emit radiation over time, which causes them to lose mass and eventually disappear. At the time, though, this radiation seemed to be random and didn't carry any information about what fell into the black hole, which clashed with the principle of information preservation in quantum theory. Scientists did try to combine quantum theory with gravity to solve this paradox, but they ran into mathematical problems and couldn't make sense of it. The situation seemed quite confusing, which is probably why the theory didn't actually pick up and somewhat disappeared as the world of science went on. However, a recent study led by Nita Engelhardt and her team made exciting progress. They re-examined Hawking's formula and found a new calculation suggesting that information does escape black holes through their radiation after all. The revised formula proposes that the radiation carries subtle traces of the lost information inside the black holes. As the black holes evaporate, they emit this radiation, revealing some details about the matter that had fallen into them. This development has profound implications, suggesting that the paradox may have a solution and that information may not be permanently lost in black holes after all. However, the James Webb Space Telescope's unexpected data has sparked debates in the scientific community. This new information is now challenging the foundation of black hole theory. So, could the James Webb Space Telescope's data support the idea that black holes don't exist at all? Could this be a game-changing moment in the history of science? For now, researchers are left grappling with these questions, working to make sense of the contradictory data and refine their models. The possibility that the universe may not contain black holes, as we've always understood them, is mind-boggling, but it also offers an opportunity to explore entirely new models of the cosmos. The world of astrophysics is bracing for a radical shift in our understanding of space, gravity, and the fundamental nature of reality itself. As the James Webb Space Telescope continues to send back data, it opens up new doors for the scientific community, particularly in the realm of astrophysics. While some of the early results have puzzled scientists, they have also raised intriguing questions about the very nature of black holes. If black holes, as traditionally understood, do not exist in the way we once thought, what might actually be causing the phenomena we've associated with them for decades? This ongoing challenge forces researchers to rethink the basic assumptions that have shaped the field of astronomy for more than a century. One possible explanation that has emerged from these new observations is the idea that the objects previously identified as black holes might be something entirely different, perhaps exotic compact objects, ECOs. These ECOs could share some observable properties with black holes, such as gravitational lensing effects and X-ray emissions, but they may not involve the formation of an event horizon in the traditional sense. Instead, they could be objects with a distinct structure that allows for the preservation of information, which contrasts with the information loss associated with conventional black holes. ECOs would still warp space-time in ways that create the same gravitational effects we've observed, but without the singularity at their cores. Another idea gaining traction is that the gravitational waves detected by instruments like LIGO may not always be the result of black hole mergers. While LIGO's groundbreaking observations have been widely accepted as proof of the existence of black holes, there is an emerging theory that some of the gravitational wave signals may be produced by other massive objects, such as neutron stars or other dense matter configurations that behave in ways similar to black holes but differ in their internal structure. These alternative explanations, though still speculative, challenge the assumption that gravitational wave detections are definitive evidence of black hole mergers. Meanwhile, a growing number of theoretical physicists are revisiting the fundamental laws of gravity itself. Einstein's theory of general relativity, which has long served as the bedrock of modern astrophysics, might not be as comprehensive as once believed. Some scientists are exploring the possibility that our understanding of gravity could be incomplete at cosmological scales. For instance, modifications to the general theory of relativity might explain some of the observed phenomena without invoking the existence of black holes. These revised models would require a new framework that accounts for the behavior of spacetime in extreme conditions. One such modification is the idea of fuzzballs, which were first proposed as an alternative to black holes in string theory. Fuzzballs are theoretical objects that may arise from the collective behavior of quantum strings, and they would not have a singularity or an event horizon. Instead, they would possess a more complex internal structure where information is not lost but rather preserved in a highly scrambled form. Fuzzballs could potentially explain the gravitational and X-ray emissions typically attributed to black holes, but without the paradoxes associated with traditional black hole theory. Additionally, there are theories being developed around the concept of wormholes, hypothetical tunnels through space-time that might connect distant parts of the universe. Some researchers speculate that what we perceive as black holes could be connected to wormholes, acting as a kind of gateway between regions of space-time. This could explain some of the strange gravitational lensing effects and the apparent inability of light to escape from black holes. If wormholes do exist, they might offer an entirely new way of thinking about the structure of the universe and the connections between different cosmic regions. Despite the dramatic implications of these findings, many astrophysicists remain cautious. The data from the James Webb Space Telescope, while groundbreaking, is still being processed and analyzed. Some of the unexpected results may be due to errors in the telescope's instrumentation or new phenomena that have yet to be fully understood. Others argue that the fundamental nature of black holes is still valid, but that new data will help refine the models we use to describe them. The idea that black holes might not exist as we have imagined them could be a revolutionary shift in our understanding, but it may also lead to the discovery of new and unexpected phenomena that push the boundaries of current scientific paradigms. Ultimately, the current wave of discoveries and theories about black holes and the nature of spacetime highlights the excitement and uncertainty that defines the field of astrophysics. As new technologies emerge and more data is gathered, the next few decades could yield even more surprising revelations about the universe. Whether or not the traditional concept of black holes survives this new era of discovery, one thing is certain: we are on the cusp of a major transformation in our understanding of the cosmos.